start. Welcome everyone to the 2020 edition of Runtime Verification, and this the invited tutorial by Laura Nancy. So my name is Thomas Ferrer. I'm a senior hardware engineer in Imagination Technologies in the UK, and I'm joined by Sarah Mohaminejad, who's at USC. And it's my great pleasure to introduce Laura Nancy, who's an assistant professor at the University of Trieste and a part-time project assistant at the University of Technology of Vienna. And she's a recipient of the Young Investigator Research Grant, and I'm told since the 1st of October of the Heidi Lama Award from the city of Vienna. So congratulations, it's very recent. So we're looking forward to hear about more about her research. Her research is in, broadly speaking, in model logic, in cyber physical systems, and in systems biology. And today she'll be talking about monitoring spatio-temporal properties. So the tutorial will last 2 hours, as you know, consists of two 45-minute parts, and at the end of each part we will have a few minutes for questions. So when it comes to question, I can ask everyone to raise a hand via the button on Zoom, or ask their question in text form on the Slack channel. If there's nothing else, we're ready to hear your talk, Laura.
Yes. As you want, yeah, I'm ready. Well,
welcome to RV.
Yeah, thank you. Good morning, good afternoon, or good evening to everybody with respect to the place in the world where you are. I'm Laura Nancy, and in this tutorial I will talk about monitoring spatio-temporal property. We have several examples of systems that are intrinsically spatial distributed, for which the spatial configuration should be taken into account when we study and analyze such system. We can see here some example. On the top left, we have a wireless sensor network. So we have a number of sensors distributed in a space that collect some data and that can be connected to each other in some way. Then on the top right, we have a bike sharing system. So think about a number of bike stations in a city where people can pick up or bring back some bike. And on the bottom left, we have a cholera spread. The cholera is a waterborne disease, so this is the spread of a disease in a space. And on the bottom right, we have the Turing pattern. So the formation of patterns that are then stable in time. So then we can see on each of them some property that could be interesting to study, as for example, for the bike sharing system, you would like to have the bike always available in each station, or maybe if in a station there are no bikes, you would like to find a station that is close to your station, so in a radius of no more than 50 meters, where you will find a bike. Or in the case of the spread of the cholera, you would like to check the spatial spread of the disease, and for example, this can be described by the property that after 10 time units, there exists a location at a certain distance from location where I'm checking this property, where the number of infected individuals is more than 50. For the wireless sensor nectar, an important property is the reliability, and this can be described, for example, saying that we can always find a path of sensor such that all sensors have a battery level greater than 0.5. And in the last one, we can take one particular type of pattern as example, that are the spots, so the formation of spots. And this can be described in words as we have some regions with a very low density of a protein A, and these are surrounded by regions with a high level of protein B. So what we will see today or what we would like to ask is how we can specify such temporal, spatio-temporal behavior in a formal and human understandable language. And also when we have like the specification, how to monitor the onset efficiently. In this tutorial, we will see a possibility to solve that issue, so a way to specify and check these properties using the spatio-temporal reach and escape logic, STREL. STREL is an extension of the signal-temporal logic with a number of spatial operators. In the first part of the tutorial, we will briefly recall the signal-temporal logic, and then we will define the input of STREL, so how we will describe the space model, so and how is defined a spatio-temporal trajectory. In the second part of the tutorial, we will discuss about the monitoring procedure, and then we will see the applicability of the logic to a number of scenarios. Let's start with the first part of the tutorial. All the examples that we have seen can go under the general umbrella of complex systems. Complex systems are systems with an heterogeneous number of entities that usually are has a nonlinear interaction between the component, and then means that usually the emergent behavior cannot be derived from the knowledge of the single entity. Furthermore, we see in our example shows also an homogeneous spatial distribution, and they are all large-scale systems. So all this complexity of this system often limits the possibility to analyze them using exhaustive verification techniques, and some common approach consists instead in simulating their design with for example, different initial condition, parameters, and inputs, and then use a monitoring procedure to check the single trajectory. So instead, what we will see in this tutorial is not about model checking, but is about monitoring. So what is a monitoring algorithm? A monitoring procedure or algorithm permit to check the single trajectory. So given a specification as a temporal logic formula, and a simulation, a trajectory of a certain model, we check if this single trajectory satisfies or not the property, and this will be the result. A logic that is very suitable to specify and check property over simulation of system is the signal-temporal logic. Signal-temporal logic, probably most of you will know, is a linear time temporal logic that extends the dense time semantics of the metric interval temporal logic with a set of atomic proposition. And these atomic propositions are inequality on the variable of the system. We can see here the syntax of STL. We have the true constant, the atomic proposition mu, the negation, the conjunction, and then the temporal operator until, phi1 until in a time between, in time interval I, phi2. And then we can derive also other two operators, the eventually operator and the always operator, and the disjunction operator that can be derived from the conjunction. So what does it mean to do a specification with a temporal logic language? So we see here a very simple example. We have a simulation of epidemic system. So we have the evolution in time of the number of infected, recovered, and susceptible individuals. And for example, we want to ask if between 30 and 50 time units, the number of recovered individuals becomes more than 60. This can be described by this temporal logic formula, where this is the operator eventually, and this means eventually in a time between 30 and 50, the number of recovered individuals is more than 60. Similar, you can describe property with the always operator, where a property should be true in a certain time interval, and then you can use the until operator to say that phi1 should be true for a certain time interval until phi2 should be true in a time unit inside the interval I. The signal temporal logic has two semantics, a Boolean semantics that gives just a 0-1 answer. So a tells just if a trajectory satisfies or not a property, and also it has also quantitative semantics that can give a value of the satisfaction. Furthermore, the evaluation is done at each time step. So as a solution, you can have a Boolean signal for the Boolean semantics or a quantitative signal for the quantitative semantics. So we say that in the signal, we know that a certain time step t of the signal is, so the signal at a certain time step t is equal to 1 if and only if the trajectory at the time t satisfies the formula. And similarly, for the quantitative semantics, you have at each time step the value of the quantitative semantics with respect to the trajectory at that time step. We call also the quantitative semantics, the function that is computed is also called the robustness. So given a certain trajectory and a certain formula phi, we can compute a Boolean or a quantitative signal that gives us the value of satisfaction, a Boolean or quantitative value at each time. How it works, the monitoring algorithm? It works working on the parse tree of the formula. So given a formula, you can derive the parse tree of the formula, where at the bottom you have the atomic proposition and at the top you have the whole formula. From this, from the atomic proposition, you derive the secondary signal. So you start with your trajectory, you compute you evaluate the atomic proposition and you compute the secondary signal, and from this you compute at each leaf of the tree, at each node you have a specific a specific operator that for which there is a specific algorithm. So each operator has a specific algorithm that you compute with respect to the Boolean or the quantitative signal, and then you derive the Boolean and quantitative signal for the next nodes, and then you go up on the tree of your formula until you reach the top, where there is the global formula. So at the end you have, as I say,
a Boolean signal for the Boolean semantics or a quantitative signal for the quantitative semantics. And then we say also that the all trajectory satisfy the formula if the trajectory satisfy the formula at time 0. What we will see with our spatio-temporal logic is that we have to add some spatial operator on the logic, and furthermore, instead to have just a temporal trajectory, that is a set of temporal signal, we will have a spatio-temporal trajectory. So we have to add also the space, and furthermore, we have to see how is shape this space. So we have also to define what is the spatial configuration. And as a solution, instead to have just the Boolean and quantitative signal, you will have also the space. And in that case, we will not have, as for the temporal case, like a 0 position. So we will have a solution for each location.
We use a running example to describe the logic, that is the wireless sensor network. So as starting point, just think to have a number of sensors in the space that are distributed in some way and that can measure some values, as for example the level of temperature or the level of pollution. For the moment, we think to have just the same type of sensor. So before describing the logic, we have to describe what are the input and the output of our monitoring procedure. So we are going to describe the spatial configuration and what are the trajectory and the signal. The spatial configuration that we consider is a discrete space, described as a weighted direct graph. Indirect graphs can be treated as direct graph with a symmetric relation. The reason why we chose this kind of description of the space are mainly two. The first is that many applications that we consider as the bike sharing system, the smart cities and sensor network are naturally framed in a discrete spatial structure. The second one is even other kind of system as a continuous space is often described as a grid or as a mesh. Think, for example, the numerical integration of partial differential equation. So for that reason, now until now, the description of a space as a weighted graph seems to have the better description that we can have. So we define a space model as a tuple LW, where L is a set of nodes that we call location, and W is a proximity function that associates a label that is a real value to each distinct pair that are connected. So you can think to this W, capital W, just as a subset of the space location times real value times location, and you say that if there is a tuple, for example L1 W L2, that belongs to this set, so to capital W, it means that there is that L1 and L2 are connected and that there is a weight equal to W. As you can see here, for simplicity, we consider undirected graph. You can see there is an arrow going in both the direction. This is the same to say that there is an arrow going from L1 to L2 and another arrows that are going from L2 to L1, and both have a label equal to W. Okay. But usually when you write L1, W, L2 means that there is an edge going from L1 to L2 with weight W. We can define different graphs on the same set of location. Here we can see an example with respect to the sensor network. This is the connectivity graph. And we say that two locations, so two sensors, are connected, so there is an edge, if and only if they are within their communication range. So each sensor has a specific radius that design a circle like around him. Where if there are sensors that are within this circle, that they can communicate. So if two different sensors have their communication range that intersect, then they can communicate, and so there is an edge between them. Another example is the proximity graph. And this is the dual graph of the Voronoi diagram. The Voronoi diagram is a partition of the place into a number of regions, and you have one region per location. And in particular, it's assigned each point of the plane to the region corresponding to the closest location. Okay. So in the case of the proximity graph, if you have really few sensor and the space is still very large, you can have very few regions here, but you will have always some connection between the sensor, even if their communication range is not intersect to each other. We define then a route. A route is an infinite sequence of location. And the important characteristic of the route is, of course, that if for each pair of location in the sequence, there should be an edge. So you can see here two examples. So L0, the sequence L0, L1, L2, L1 is a route, because as I say, we are using undirected graph, and here we can find an edge that goes from L0 and L1, one from L1 to L2, one from L2 to L1, so we can go back. Instead, the sequence L0, L1, L2, L3 is not a route because there is no edge, no edges that goes from L2 to L3. And then just to know, we denote the IT nodes as tau I with the square bracket, and instead we define the first occurrence of a location in the route with instead the round bracket. So tau L is used to denote the first occurrence of L in the sequence tau. So just to understand, tau L in the sequence L0, L1, L2, L1 is equal to 1.
We can use routes to define the distance among two locations. And to do this, first we define route distance, and then we define distance between locations. So the distance is computed using an appropriate function f, and we will see some example later. And this function combines the different weights in the root into a value. So, and it's done in a recursive way. So you define a distance upon a certain index, and then actually you decrease the IT for at each iteration until you reach the I equal to 0. But we will see this in the next slides with an example. And just to know, so the distance on a root is defined with respect to the index. You can define the distance with respect to a specific location, and this corresponds to consider in the root the index that corresponds to the first time that this location is considered in the root. Let's see two examples of this function f that we can see here. One is the weight, that is just the sum of the inputs. So this corresponds just to sum the value of the label of the weight in each edge. And another possibility is, for example, the OPS, where you are not going to count to sum the value in the edge, but you are just summing one for each edge. So what you are going to doing here is to count the number of OPS that you have in the root. So let's see one example of computing the distance. So here we are computing the distance considering the weight function and up to the index 2. So you're going to compute the function weight considering here is the value of the first edge that goes from L0 to L1, that is 4. And here you are going to consider the distance of the root from the next step, so from L1, and decreasing by 1 the index, so from 1. Then here is just the sum, so you sum here, and here you are doing the same again. So here you are going to consider the value of the edge from L1 to L2, that is 2, and then you are going to decrease again from 1 to 0 the index, and you are going to consider the root not from L1 but now from L2. And then again you are going to sum them, and when we arrive to 0, the value of the distance is equal to 0. So you have 6. That is exactly the sum of the weight in the root. Similarly, if you do the same, consider the OPS function, what you have at then here is just 2, because you have summing 1 on 1 2 times, and that is exactly the number of OPS that you have in the root. Then you can define the location distance that correspond to what is the distance between two locations, that correspond to the minimum considering all possible routes that start from Li and goes and ending to Lj. So for example, taking the previous example, if we are going to see the location distance from L0 to L2, considering the OPS distance and all possible routes, in this case we have just the value equal to 2. But for example, if you add an edge that goes directly from L0 to L2, then this value will be equal to 1. And finally, we define the signal and the trace. The signal is just a function that associates at each location a temporal signal, where D can be different things, can be a Boolean set, or can be the real value, or maybe can be also integer values. So you have a different possible signal, a Boolean signal, a quantitative signal, or an integer signal. And then we define the spatial temporal trace or trajectory as a vector of temporal signal. So, for example, if you think again to the sensor network, the spatial temporal trajectory means to consider, for example, the value of the temperature in each location in time, and the value of the battery. Finally, as I said, we can consider both static and dynamic spatial configuration. So what we defined at the beginning was a static spatial model. But we will see also dynamic spatial model. In the dynamic spatial model, what you have is just a different possible space model at each time. So we will denote the dynamic spatial model just considering S as a function that will give at each time step t a specific spatial model Si. Since we will consider just constant piecewise constant signal, you consider to have the same space model until the next time step. And here we can see just an example of two different space model of the same sensor network system, where you can see that the spatial configuration, so the number of edge and the type of edge change in the two different time steps. Okay, now we are going to define the logic. The spatio-temporal reach and escape logic STREL is an extension of the signal temporal logic with a number of spatial operators. Here we can see the syntax of STREL, where true is the Boolean true constant, mu are the atomic proposition, then we have negation conjunction, the temporal operator until and since, and then you have the spatial operator reach and escape. Then we can derive other operators, the disjuncture operator and the temporal operators eventually, globally, once and historically, and then the spatial operators somewhere, everywhere, and surround. To describe the spatial operators, let's consider a simple graph, as you can see here in the slide, where the color in the node correspond to an atomic proposition that is satisfied by that node. Means that we consider to focus only on spatial operators, we consider as atomic proposition colors. So, like the yellow atomic proposition is satisfied by all the nodes that are yellow. And similarly, the blue proposition is satisfied by the nodes by the location that are blue, and so on. So in this way, we focus in understanding just the spatial operators. The first operator that we see is the reach operator. The property phi1 reach phi2 at the distance between d1 and d2, considering the function distance f, describe the behavior of reaching a location that satisfy the phi2 property, passing only through a location that satisfy phi1, and such that the distance from the initial location and the final one belongs to the interval d1, d2. A bit more formal, considering a spatial system S and a spatio-temporal trajectory X, we say that that system in location L at time t satisfy the reachability property if and only if it satisfies phi2 in a location L prime that is reachable from the location L through a route with a length that belongs to d1 and d2. The length that starts from L, and that we are considering the route from L to L prime, and all its elements with index less than tau L prime satisfy phi1. So we have a route that goes from L to L prime, and all index before L prime satisfy phi1, and the L prime, the route at index where there is L prime satisfy phi2. Let's see an example to better understand the operator. So here we have a graph, and we want to see if there are locations that satisfy the property yellow, rich, pink, in an interval between 1 and 4, considering the Hopf function. So to simplicity, in this example, we use just the Hopf function. So we are just considering the edge all with the weight all equal to 1, and not adding further like value to make the things simple. So let's see, for example, here we can see that the location, for example, L3 satisfy the property that yellow reach between 1 and 4, pink, because we can find a route, for example, L3, L13, L14, L17, L35, where the location L35 satisfy the pink property. All previous location of the route satisfy the yellow property, and the distance from L3 to L35 of this route is 4. So it's less than the upper bound of our interval of the interval distance. Instead, if you can see L4, so the location L4, so that one, does not satisfy the property, because the distance of the route of this route to L35 is 5. So it does not belong to the interval, and so the property is not satisfied. The escape operator, escape phi, at the distance between d1 and d2, considering the distance function f, describe the possibility of escaping from a certain region, passing only through a location that satisfies phi, via a route with a distance that belongs to the interval d1 and d2. So a spatial model S and a spatio-temporal trajectory X satisfy this escape property in location L at time t, if and only if there exists a route tau and a location L prime that belongs to the route, such that the first element of this route is L, and in the distance, the route distance between the location L and L prime belongs to the interval D1 and D2. And all elements in the root from the first element L to the element L prime satisfy phi. So let's understand better the operator with an example. We consider the property escape, the orange property, at a distance more than 3, considering the distance, the hop function. So we can see, for example, that the location 9 satisfies the property, and we can see together why. So we can see that there is a root L9, L10, L11, and L12 that as a first element, it has as first element L9, and there is an element that is L12, such that the distance between L9 and L12 is 3. 1, 2, 3. And all elements satisfy the orange property. Okay. We can see instead that, for example, L10 does not satisfy the property. Why? Because we cannot find any element such that the distance between L10 and this other location is more than 3, and all the elements satisfy the orange property. We can see that the maximum that we can have is a root with 2 at the distance of 2. So there is no elements at distance equal or greater than 3 where all the elements where there exists a root with this element, and all the elements satisfy the orange property. So these were the operators of the logic, and then we can of the basic operator, and then we see the operator that can be directly derived from these two operators. The first one is the somewhere operator, and the meaning is really simple. The meaning is that from a certain location, the property somewhere phi at the distance between D1 and D2 is satisfied if there exists an element at the distance between D1 and D2 from phi where the property is satisfied. So let's see this directly with an example. Somewhere pink at the distance between 3 and 5, considering the Hopf function, is satisfied, for example, by the element L1, because there is a location, the L35, that satisfies the pink property that is at the distance between 3 and 5, because you can see there is a root 1, 2, 3, 4 that permit us to arrive to reach P at the distance below that more than 3 and less than 5. Then we see the everywhere operators that instead to say that there exists a location at a certain distance from where I'm checking the property that satisfy the property phi, we say that all the location that belongs to the interval D1 and D2 must to satisfy the property phi. So a spatial model and a spatial-temporal trajectory satisfy the everywhere property if and only if in location L at time t, if and only if all the location L prime that are reachable from L via a path with a length that belongs to the interval D1 and D2 satisfy phi. So here we can see, for example, that L1 still satisfy even this property because all the elements that are at the distance between 2 and 3 satisfy the yellow property. And instead, for example, L2 does not satisfy the property because there is an element, a location, L18, where the distance is still less or equal to 3, but the property yellow is not satisfied. And finally, we see the surround operator. So phi1 surround phi2 at the distance d1 and d2, considering the distance function f, expresses the topological notion of being surrounded by a phi2 region while being in a phi1 region with some additional metric constraint that now we see more in detail. So the idea is that you have a phi1 region that is surrounded by a phi2 region. We say that a spatial model and a spatio-temporal trajectory satisfy the surround property in location L at time t, if and only if there exists a phi1 region that contains L, and all the locations in that region satisfy phi1 and are reachable from L via a path with length less than d2. And so in this way we describe the phi1 region. And then we say that all the locations that do not belong to this phi1 region, but that are directly connected to a location in that region, must satisfy phi2. And we have then the metric, the distance, the metric constraint that say that all these locations that are directly connected with some location that belongs to phi1 must be reached from L via a path with length in the interval d1 and d2. So what's the idea is that all the elements that belongs to the phi2 region are anyway inside the ring d1 and d2 as a distance from the location where we are checking the property, that is L. So let's see also this one with an example that can help to clarify the operator. So we consider in the property green surround blue at the distance between 0 and 100 with considering the hope function. And we can see that in that case all green points satisfy this property. Why? Because for each green point we can find a region that contains that point such that all its points are green and all the points connected with an element that belongs to that region are blue and satisfy the metric constraint. Why? Let's, for example, consider this location, 47. So we have a region that is the green region, where all the elements are at the distance between 0 and are at the distance less than 100 from the location L47 for sure. And then we can see that all the location that does not belong to the green location, the green region, but that are directly connected with that region, they are blue. And for sure they are at the distance that is more than 0 and less than 100. To better understand the distance constraint, let's see the same property but with a different distance interval. So instead of 0, 100, we have 2 and 3. In that case, the only location that satisfies that property is the location in the center, so the location 43, because it's the only one for which there exists a region, the green region, where all the elements satisfy the green property, and they are at the distance less than 3 from the location 43. And all the elements of the blue region, so the ones that are directly connected to the green region, are at a distance between 2 and 3 from the location that 43. All the other are the distance has some element at a greater or smaller distance. With this, we finish the first part of the tutorial, and we will see later for the second part.
We got questions from the audience. We have a few minutes for a question on the first part to Laura. I believe you can use the reaction button to signal or just send a message in the chat or on Slack. We're ready to take questions. So I think we can start with the first question from Dayan on the Slack channel, if that's okay. So the question to Laura is, can you take advantage, any algorithmic advantage if your spatial specification has a specific regular form? So if space is regular in I guess in the sense of finite automata theory, can you, or rather the specification has a regularity?
I have to think that until now we treat like the grid as an indirect and as a graph, so we didn't take any advantage for it. So actually we didn't think about this point. I don't know actually, because for now the algorithm works in reaching a fixed point, and we will just pretty briefly discuss in the next tutorial. And so it's going up on the taking the neighbor of the neighbor of the neighbor until it finish the configuration. So more edge you have in the graph, more like is high the computation. So we can say that if we have a spatial configuration with not many edges, or that probably the algorithm is faster, but we didn't like construct any specific algorithm for specific configuration. I would say that it comes from directly from the algorithm that we have. If Michele wants to add something, it's always he can say something more. It's here.
I want just to add that yes, currently we focused only on general graphs, and without taking into account any form of regularity, so grids or similar things. However, it's clear that we can tailor our algorithms to work with the specific forms of the graph. And I think that this could have some advantages, for instance, in grids, for the grids, for computation of some of the results of the monitoring or the runtime verification. But this is part of a future work in some sense.
Sounds interesting. Have we got other questions at this point from the audience?
Yeah, there is one question I can see. I can read it maybe. Just trying to get where you are going to go next. Would it be like a statistical model checking approach in time, so that you are going to pick up sequence randomly and then verify them by one instead of performing complete? Yes. In the second part, we will see one of the case study, the bike sharing system case study is considering a stochastic system where we are doing statistical model checking. Yes, so we are going to count in that case the probability satisfaction of the property. And we have other case study when we have considered also the quantitative semantics, so the average robustness. So yes, what we are doing is, as for STL, is for stochastic system, we're using statistical model checking.
Okay.
I have a question, if you don't mind.
Yes.
Yes,
please.
sure.
So if I understood correctly, your spatial structures are instantaneous in a sense, right? So you are describing kind of the current state of the graph, if you will.
Yes.
Have you considered the case where, you know, navigating the graph takes time?
Yes, that's why we have not yet online monitoring, and we are working on it. So this is offline monitoring, so we know that it takes time, and now we are working in trying to have an online monitoring, be faster and parallelize the computation on the spatial part that is most costly, costs more than the temporal part. But yes, so until now, this monitoring is just offline. So it takes time, but having offline monitoring is not a problem.
Well, no, I think that the question may be slightly different, right? So it is really what you want to describe. So for example, you may have a situation where you have, well, essentially sensors in all nodes, and they communicate instantly. In that case, you can essentially assess the instantaneous state of the spatial structure. And sometimes you don't, and you have to navigate. And so that's kind of the behavior.
So you mean if you have a distributed system, so we don't have the information at the same time in each location.
Exactly.
That's even more complicated. So that will be the future work when we finish the online monitoring. But yes, that's there are some work on trying to do a monitoring on distributed system. But yes, the main problem is that your graph can change when you have just the information of your neighbor. So you will never have a like exact solution of your system. Yes.
Sure. Okay. Yeah.
But
thanks.
yes, that's a very good question, and we would like to arrive to a good algorithm in some years on also in this part.
So I can thank you for the question. I can see a few more, few raised hands actually. So we are already running over a little bit. So, but let's try to take a couple more questions, and then we can go on a short 5 minutes break. We have a question from Panagiotis. If you would like to ask your question, thank you.
Thank you very much. Thank you, Laura, for the nice presentation. I would like to make a question focused on the expressiveness of your logic. In the beginning of your presentation, you showed us some very interesting examples from different requirements, specifications from various applications. I wonder if you have experience with working with such diverse requirements from many different application fields in order to have an idea of the expressiveness and the generality of this spatial model representation.
Well, in the second part, we will see 3 of the case study that I presented at the beginning. So with some example of property that the logic can express. And the third one, the epidemic one of the cholera study, we have in one paper, but there was no time to put 4 case studies. So we have some example of each of them. But I think, yes, the operator are really general. So you have just to use your imagination to think to different property. I mean, this is even probably the most difficult part, to think how to use them. And it's also it's difficult for us sometimes to define the good spatio-temporal property in the system with the logic.
And have you also studied the theoretical properties of these operators? I mean, your logic language, equivalency relations, and all these things.
We have done some example of equivalence in the first paper, but then we stopped that part. We are more focused on try to use it in a real application then.
Okay, thank you very much.
You're welcome.
And if we can take one last quick question from Joshua.
Yes, thank you. So I was wondering about the escape operator. So if I understood correctly, there has to be another location within a certain distance, and there has to be a trace from the current location to that location where the formula phi holds on every node, roughly.
Yes. Mm-hmm.
So what confuses me is that you have both this minimal distance and you have this path, but this could go in a different way than like the minimal connection.
Yeah, we have to the operator. The reach operator is without the minimal distance. So the idea is that you have to reach a certain location where all the paths satisfy the first property and the last one satisfy the second. Instead, the escape operator is the one that is taking into account that this should be like this. In that case, you have to consider it the minimum distance. So you need that you can escape with having at least the number of nodes that so the minimal distance is, so you are sure that you always true that you pass at least for that number of nodes. That's why you need the minimal distance. So the fact that you have the minimal distance is used that to know that in each path that you can take, there should be that number of nodes to go out. I don't know if I answered to the question. Maybe we can see later, I can show you the semantics and we can see together what's the difference between the two.
Okay, sounds good, thank you.
So at this point, we are going to take a short 2 minutes break. And okay, so I think we'll just resume right away, if that's okay with you, Sarah.
Should I start playing?
Yes, please.
Okay.
So that's
in the second
part
of the tutorial, we will discuss a bit about the monitoring procedure, and then we will see a number of application of the logic to different scenarios. In particular, we will see 3 different scenarios. One considering a static space and a regular grid, where we study the formation of patterns. Then a scenario with a static space and a stochastic system, where we study the availability of bike in a bike sharing system. And then one with a dynamic space, where we're going to describe the connectivity and reliability in a wireless sensor network. Until now, we designed just offline monitoring algorithms, and similarly as STL, STREL has 2 semantics, a Boolean semantics that tells at each location and time step the Boolean satisfaction of the property. So as for STL, we have a spatial Boolean signal S, such that the signal is in location L at time t is equal to 1 if and only if our space model and spatio-temporal trajectory in location L at time t satisfy the property. We don't have as STL is all one value for the whole spatio-temporal trajectory, but we consider a spatial Boolean satisfaction that corresponds to the satisfaction at time 0. So given a spatio-temporal trajectory, we can give as answer the whole spatial Boolean signal, all the spatial Boolean satisfaction, at time 0. Then we have also a quantitative semantics where we have evaluation of the satisfaction. And in this case, so we can have a spatial quantitative signal that give at each location and times units the value of the robustness function for our spatial model and our spatio-temporal trajectory in position L and at time t. And similar, we can define the spatial quantitative satisfaction that correspond to the satisfaction in each location at time 0. So what we have in all is as input we will have our spatial configuration, just one configuration. If we have a static space or a dynamic configuration where you have a different graph for each time unit and a spatio-temporal trajectory. Then we have a specification, our formula, and given this we have, computing the monitoring algorithm, we have as a solution a spatio-temporal satisfaction or a spatial satisfaction. So as for STL, the monitoring algorithm work on parse tree on the tree of the formula, where we have at the bottom our spatio-temporal trajectory, and then each node corresponds to a sub-formula, so to a specific operator of the formula that we are considering. And then we have a different algorithm for each operator. So what we have done mainly is to extend the evaluation even for the temporal operator to spatio-temporal trajectory, and then in particular we add the algorithm to check the spatial operator. Just a consideration about the computational cost for the temporal operator. We are using algorithm like the STL monitoring algorithm, and they are linear in the length of the signal times the number of locations in the spatial model. Instead, the spatial properties are more expensive, and they are based on a variation of the classical Floyd-Warshall algorithm. And the number of operations to perform is quadratic for the reach operator and cubic for the escape operator. As a first example, we consider a scenario with a static space and a regular grid. We want to study the formation of pattern. To do that, we consider a reaction diffusion system that describe the production of skin pigments that generate spot in an animal force. In particular, there are two proteins that diffuse in the space and react with each other when they are in a connected cell. Here you can see in the video the evolution in time of the system, and you can see that after a certain number of time units, there is a spatial configuration that is stable in time, where there are a number of spots in the space that are almost equidistant from each other. And here we see just the evolution in time of the concentration of the protein A, where in the spot, so in the blue part, the concentration of A is very low, and in the red part, the concentration instead is high. As a space model, we consider the regular grid, and we treated that hit as a undirected weighted graph, where each cell of the grid is the location, and we consider to have edges between connected cells. So between cells that are neighbor in all four directions. And we consider to have only one label which corresponds to the hop distance function, so that is equal to 1. So if two cells are neighbors, then the distance is equal to 1. The spatial temporal trace describes the concentration of the protein A and B in each cell of the grid at each time step. And this is generated by a reaction diffusion system that we discretize according to a finite difference scheme as an ordinary differential equation, where the variables are exactly the cell of our grid. Okay. As first property, we want to describe the formation of the spot. We can use, to do that, and probably you will guess it, the surround operator, because it's very, it works very well to describe regions that satisfy a certain property and that are surrounded by another region that satisfy a second property. So we can describe the formation of spot using this formula. That means eventually, in a time between 19 and 20, so in the time when the system stabilizes, it's always true from that time that this property is satisfied. That means there is a region where the location where I'm checking the property belongs, where A is always less or equal to 0.5, and that region is surrounded by another region where all the nodes that belongs to that region satisfy the property A greater than 0.5. Furthermore, from the region, the location where I'm checking the property, all the location of the first region should be at the distance less than W2 from the location where I'm checking the property, and all the region of the second, all the location of the second region should be at the distance between 1 and W2 from the location where I'm checking the property. If you remember, we say that we are checking the property in each location. And here we can see the solution that corresponds to the satisfaction at time 0 in each location. So on the left, we can see a snapshot of our system of the concentration of protein A in each location at time 50. In the center, we can see the Boolean satisfaction, and on the right, we see the quantitative satisfaction. In the first line, we consider a distance constraint W2 equal to 6. Instead of the second line, we consider a W2 equal to 4. So you can see in the Boolean satisfaction, the location that satisfy the property are the location red, and the location blue are the location that do not satisfy the property. You can see that in the first line, almost all the location that correspond exactly to the spot, so to the blue part on the trace, on the snapshot on the left, satisfy the property. Instead, on the second line, you can see that if we restrict the bounding constraint, if we restrict the distance constraint, then almost the only location that satisfy the property are the location in the middle of the spot. And sometimes even there are some spots that are missing because they are not very regular, and so any of of its location satisfy the property, the distance constraint. Instead, on the right, you can see the quantitative satisfaction in each cell. And in the color correspond to the color of the legend. So the maximum value where the property is satisfied is anyway very close to 0, and this is because we are using just the protein A, and here we are considering one property that should be less than a certain value and this property greater than the same value. Okay, here, so in the previous slide we have seen a local property to define the spot, but what we would like is something to define the whole pattern. A way to define a global property using this operator is using the everywhere and the somewhere operator. So we can describe the whole pattern with this property. That means everywhere. So in each location, from each location should be true that from that location I can find a location at the distance between 0 and 50 where the property phi spots formed, so the formation of spot property, is satisfied. So this means that each node in the grid should be connected to a node at a distance less than 50 where the spot property holds. And the 15, so this value corresponds to the maximum distance between the spots. So in this way we can describe a global property. Why? Because the everywhere operator without a distance constraints permit us to cover all the location of the grids, and the solution in each location will be the same. So it's enough for us to see one location and see the satisfaction in that location to know that this will be the same in all the locations. Here we can see 3 different patterns that we can derive from the same reaction diffusion system, changing the diffusion constants. The first one is the ones that we have seen before, and that permit us to have a pattern with the spots. If we change just a bit the diffusion constant, we can have very different patterns as the one in the middle, and some similar but with a bit different kind of spot as the one in the right. If we check this property on this different spatio-temporal trajectory, we can see that only the first one satisfies the property. Instead, if we check just the formation of spot property, particularly the last one has several locations that can still satisfy the property. With this last property, we would like to show you how we can nest temporal operator within spatial operator. We are considering here a perturbation property. To do that, we have perturbed our system. So we are considering the same reaction diffusion system, and instead to take totally random initial condition for protein A and B, we consider as initial condition the value of protein A and B at equilibrium. So when there was the formation of the pattern. And then we perturb just the value of one cell that you can see here in red, from a very low value to a very high value. Higher than the maximum value of all the other location of both protein A and B. So that means that it was the only location with the value greater than 10, greater or equal than 10. And why we have used such a high value? Because to perturb the system, but also because in that way as you can see now on the property, the only location that can satisfy the property the value of A greater or equal to 10 is the one that we have perturbed. So the property that we are considering is this one, where in the first part there is this atomic proposition, and if you remember, we are going to check then the satisfaction of the property at time 0. So the only location that can satisfy this property is for sure the location we have perturbed, because all the other has the value that is less than 10. And then for sure it is the only one that can satisfy, but it should satisfy also the second part. The second part, we are using again the surround operator, and this means phi absorb surrounded by phi no effect at the distance between 1 and 2. What does it mean this? So the first part, the property phi absorb, that means eventually in a time between 0 and 1 is always true between 0 and 10, then the value of A is less than 3. So this means that in one time unit we want that the value of our cell 6 is already going to less than 3 from 10. So we already want that most of the perturbation is already absorbed. And the second part, the property no effect, means that this means always between 0 and 20 that the value of A means should remain less than 3. It used to be sure that the perturbation remains confined inside the original spot without going out. Okay, so here we can see the evolution in time of the trajectory, and you can see that the perturbation is easily absorbed by the system and is not going out from the spot. Indeed, if we check the property is satisfied by the trajectory. As a second example, we consider a scenario with a static space and a stochastic system. STREL can be applied on stochastic system considering methodologies as statistical model checking. Statistical model checking combines simulations of the stochastic system. That means an algorithm that samples the trajectories according to the probability distribution of the model with different possibilities. For example, we will see in this case that we describe the system considering a continuous time Markov chain. So the statistical model checking combines this stimulation of the stochastic system with stochastic model with a monitoring routine for the property feed, the ones that we have seen before, not the single trajectory. So the idea is that a stochastic system, a stochastic process can be described as the set of the all possible trajectory that it has, so the trajectory space. And on this is defined a probability measure on a certain sigma algebra of the trajectory space. This is something that we cannot compute exactly, so what we have is an approximation. So we cannot compute exactly so we cannot find exactly the fraction of the trajectory space that satisfy the property, but as we say, we can do it for a subset of this, where we check a subset of the trajectory space, and then we approximate the satisfaction probability. That means the probability that a trajectory generated by the stochastic process satisfies the formula phi. In a similar way, but we are not going in detail, just think that in a similar way we can define a robustness distribution with respect to the quantitative semantic instead of the Boolean semantics. So for example, if you think to the beginning of the just the deterministic integration or the deterministic result of the numerical integration of the infected recovered individual system, the epidemic system. If instead of the deterministic system we take a stochastic system, we will have a number of trajectory. We can compute for each of them the value of the robustness, and then we can see the frequencies of this. This will give us an approximation of the robustness degree. We consider a bike sharing system. A bike sharing system is composed of a number of bike stations that are distributed over a certain geographic area. And each station has a fixed number of bikes and of bike slots. And the user can pick up a bike, use it for a while, and then return it to another station in the area. We consider the bike sharing system of London. That is a very big, large bike sharing system. With we have more than 700 bike stations, each with 20-40 slots, and a total population around 60,000 agents. So that are the users that can pick up and return the bike. From that, we model it as a population continuous time Markov chain with the time-dependent rates, and to fit the parameter of the system, we use historic journey and bike availability data. And the model, so given the number of bike free slots in a station at a certain time t, what we can do is to compute the probability distribution of the number of bikes and free slot in the next 40 minutes. So we can predict the evolution of the system for around 40 minutes. The spatio-temporal trajectory corresponds to the evolution in time of the number of bikes and free slot in each bike station. And instead, the space model corresponds, so we have as a location the bike station, so the set of location L is the set of bike station, and the edges describe the connection between each station. And we say that two nodes are connected if they are at a distance less or equal than 1 kilometer. So if their Euclidean distance is less than 1 kilometer. And this corresponds also to the value of W of the label in the edge. So what we would like to check is the availability of bikes, and the idea of this property is to give the possibility of the user to consider if in the place where there is no bikes, to know if there are some bikes in some close station. The property that we want to consider is this one. Always true, that these two properties, so these two properties should be always true at each time step. The first one means that somewhere at the distance between 0 and d, the number of bikes is greater than 0. With weight, we have the distance function that we have seen at the beginning that just compute the sum of the value of the weights. And I didn't see before, but the W, if you have seen in the formula, the W that we have in each label corresponds exactly to the Euclidean distance between two different stations. In the second part, we have the same, but instead to have we have at least one bike, we ask if we have at least one free slot. So we are asking both to know that each bike is never full and never empty. What we are changing, that we are going to see now, is the value of D. So this is the distance where we are going to check if we have a station where there are at least one bike and one free slot. So what's the idea? The idea is that at time 0, when D is equal to 0, what we are checking is just the location, is just the station that where we are checking the property. So this will be just, it's always true that in the location that we are checking, there are always at least one buy and one free slot. And as you can see, there are many stations that do not satisfy the property. This figure that you see here approximates the satisfaction probability for 1,000 runs. As you have seen, we are considering a stochastic system here, so we cannot check just one trajectory, but what we are doing is to take a number of runs and to do the average and the approximation, and we can see that anyway the standard deviation is really low. So here you can see the value of the probability satisfaction that goes from 0 to 1 in the legend, and the location red are the ones that do not satisfy the property, that have a probability equals to 0, and the one blue are the ones that are always true in all the runs. So the first one is with D equal to 0, the second is with D equal to 100 meters. You can already see that we have less, so we are increasing the location that satisfy the property. And things are much better already with the 300 meters. That means that from each location, doing just 300 meters, in almost in all the location you have a probability at least greater than 0.5 to find a bike. And with the 600 meters, you can see that all the location has at least 0.5 probability to find to satisfy the property. In this figure, we can see the evolution of the satisfaction with respect to the distance of some specific location, and you can see that around 0.5, all the spatio-temporal trajectory and all these locations satisfy the property, where this dot line is the standard deviation of each for each location. As last property of this example, we are adding something to the previous property, because if you think the previous property was just considering a spatial property that should be always true, but that means that a certain user, you could know that at that time where the property was checked, there was some station with a free bike and free slot, but for sure he needs a certain time to go from his position to that station. And it could be that in the walking time that he's arriving there will be no more bike or no more slot. So for this reason, we add to the property a temporal part nested. So instead to have just that from a certain location, it should be always true that a certain distance there is a free bike and free slot. We are saying that from a certain location, it should be always true that eventually at time tw, the number of bikes should be greater than 0 and the number of free slots should be greater than 0. So we put together this the facts that we want that there are free slots and at least one bike, but this can be also treated in a separated way since maybe some user needs just one of the two. So this was just to make a global description with one property. So what is this TW time? This corresponds to the walking time to go from one place to the other, and it depends on the different distance that we are considering. So we are considering in this case an average walking speed of 6 kilometers per hour. So that means that if we are evaluating a distance of 0.5 kilometers, then we are considering a walking time of 6 minutes. The result of this of checking this property over our bike sharing system give similar results of the previous property. So that means that in that case, for the things that we have chosen, there is no much difference between looking at time 0 or after the walking time. As last example, we consider a scenario with a dynamic space. So this is similar to what you have seen at the beginning. So we are considering a sensor network, but it's a bit more complicated. So in that case, we are considering a mobile ad hoc sensor network, and this system can consist of thousands of mobile devices that are connected. And that are using to monitor different things as pollution, or temperature, humidity. And each sensor is equipped with some data processor or embedded battery. And this sensor can move independently in the space in any direction. And for that reason, they can change the links and connection with respect to the other. So in this system, we consider so we have three different types of sensor. There is the coordinator that is represented here with blue, this one. And is the unique node that is like responsible to initialize all the network. And then after this, it behaves as a router. Then there are the router that are this one. And they are like the intermediate between the coordinator and then the end devices, and they are passing the data between all the devices. And then there are the end devices that are the one in yellow, this one, and they can communicate only with the coordinator and with the router. And and is enabled to relay data from other devices. As you remember, we have seen two different possibility of graphs, considering this sensor network. And now you are seeing the evolution in time of the connectivity graph. And now you see on the right instead the evolution in time of the proximity graph. You have seen when you have very few nodes, the connected graph can have many nodes that are not connected. Instead, the proximity graph is always connected. All the nodes are in some way connected in the space. If you are considering much more nodes, you can see that the situation is different, and is the connectivity graph that has much more connections. Instead, the proximity graph will remain always with the same proportion of connection. The SASP model consists of, as a location, the devices. So the set of location are the set of devices. And in that example, so in the next slide, we will see properties that are considering just the connectivity graphs. But if you are interested in see other property or example, please contact me, or you can ask me during the question and answer time. So here, considering just the connectivity graph, we say that there is an edge between two locations if and only if the Euclidean distance between the two locations is less than the minimum between of the two communication range of Li and Lj. As spatial-temporal trajectory, we consider the evolution in time so the temporal signal in each location of three variables. The node type that actually is a constant in that case, the level of the battery and the level of the temperature. The node type is 1, 2, 3 to denote the coordinator, the router, or the end device. Anyway, in the property we will write directly coordinator, but in the implementation there is the node type. So actually the codomain is the integer set times real set times real set. In the first property, we're going to specify a connectivity behavior of our system. In particular, we want to specify that an end device is either connect to a coordinator or can reach it via a chain that of at most 5 routers. The reason why we are checking this property, we are specifying this property, is because we say that the end device should be directly connected to a router because it's the only one that can share information with it, and it should reach at a certain point the coordinator, because the coordinator is the one that starts everything. So we want that the device is connected to a router that should be connected to a coordinator, or the device can be directly connected to the coordinator. This can be described by the phi-connected property, phi-connect property, that specified the property device reach in maximum 1 hop a location that satisfies this property, so that is a router, reach in maximum 5 hops a coordinator. So this is satisfied by a location that is a device and can reach a location that is a router, or can reach a coordinator in maximum 5 hops, where in each hops it should satisfy the router property. One problem that can be this property, that can have this property, is that maybe we are not sure that this should be so it can happen that we have a connection that is broken, but the important part that is that this is always restored at within a certain time units, and this can be described by this second property, where so we add some temporal requirement that describe this fact that if you have a broken connection, this is restored within a certain time units. So we are asking that is always true, that if a connection is broken, this implies that eventually in a certain time the connection is restored. In this slide, we see the evolution in time of the Boolean satisfaction of the first property in the previous slide, so the one just with the spatial operator. In blue, there are the nodes that satisfy the property. Instead, in red, we have the nodes that do not satisfy the property. And since we have a property with just spatial operator, no temporal operator, then the length of the Boolean signal is the same as, so the final time is the same as the final time of the trajectory. As you can see here, we have a snapshot of the final time of the spatio-temporal trajectory, and we can see that the only node that does not satisfy the property is this, the L14, that corresponds exactly to the node, the only node that is just directly connected with the end device and is not connected with the routers or the coordinator. Another property that one could be interested in monitoring is the ability of the system to forward a message at a given distance. The ability of a component to forward a message is related to its, for example, battery level. And so one possibility is to consider this property. So from a given location, we can find a path of Hope's length at least 5, such that all nodes along the path have a battery level greater than 0.5. And this can be described with the escape operator. And we can say that the locations satisfy a property if it can escape with a battery level greater than 0.5 at the distance greater than 5. The battery level can be considered also for the reliability in a manet. For example, we may also want to know if there is a path to the router which is reliable in terms of battery levels. For example, a battery level above, as again, 0.5. This can be described by this property, where we are asking that not just the router reach the coordinator, but it should reach a coordinator with a path where each router has a battery at that is above 0.5. Then we can consider instead just that the device should be connected to a router or it should be connected to a router that is connected to a coordinator, we can consider this reliable router that is connected to that is reach in one hop, a reliable router. With this, we finish the tutorial. The spatial temporal property as some monitoring that I could show you. If you are interested, please contact me, and we can see other possible applications that we have in mind. And furthermore, there is a tool. Moonlight is a Java tool, and actually in this conference it will be presented a MATLAB interface that you can use for specifying and monitor STREL property. And yes, this is the website. So that's it. Thank you to everybody, and see you soon to the question and answer session.
Thank you, Laura, for this very interesting tutorial. And we have time for one or two more questions. So thank you to everyone for your questions at the end of the first half. And now we have time for one or two more questions.
So as a host, I'm not allowed to raise the hand. So can I hijack?
Yes, please go ahead.
Your specific, so your actual systems change, the spatial information changes slowly over time in many of the applications, right?
Yes.
Would it make sense to somehow encode the diff instead of the full state in every over time?
Yes, of course.
Did you think in this direction? Did you try to do anything in this direction?
For the offline monitoring, no. But now that we are working on the online monitoring, one thing is to think just to add the information of the nodes that are changed. So in the position and the edge that change with respect to change again everything. But for this moment in the algorithm, you have to again add all the information of the list of edges. But yes, for the online, we are thinking on this, and of course, there are many things that we can do to speed up the computation on the spatial part, even that considering if, for example, if you're interested in one specific part of the graph, you can even, we are thinking to have just a monitoring on that part, and so adding just that information. But yes, that's not there yet in this implementation. But yes, we are thinking on this. Thank you. I think there is a question of Gio that is written.
Yes, Gio, do you want to ask it again, maybe? We can't hear you right now, or at least I can't.
I can read the if you want. No. Yes.
Go ahead, read. Okay, you can hear me?
Yes.
Okay. So my question was more about that if you don't have this is probably for the first half of your tutorial, that if you don't have an explicit graph structure, but if you have kind of just points in space, then can you somehow implicitly construct a graph and monitor on that graph?
Well, with the both example of the sensor network and the bike station, I designed a graph. So I took the position in the space, and then for example, for the bike sharing system, I decided to put edges just if the two stations were at the distance less than 1 kilometer. So I choose the graph, and similar for the sensor network, you can even consider different graph that you can be interesting. So for example, the connectivity graph where you consider the radius, but also just adding the Euclidean graph where you have just connection with respect to the distance of the. So actually, the first version of the logic is much more general, in the sense that you can consider to have different W function at the same time and using in the property. This is not in the implementation yet, but the idea, yes. And also the distance function you can have different distance function at the same time on the graph. So yes.
quick follow-up would be that because some of your operators depend on the neighbor relation, and the neighbor relation kind of depends on the graph, is the choice of the graph that you pick going to affect whether you satisfy or not satisfy a property? And is that a problem?
Well, I think it depends on what you want to specify. But yes, the definition of neighbor depends on, so the graph, the construction of the graph depends on what you have designed. So yes, you should be careful to choose the right graph with respect to what you want. But yes, I think if I answer.
Thanks. Yeah, that answers my question. Thanks.
Right. Thank you again to Laura. I think this is all we have time for. So yeah, thank you again. Yeah.
Thomas, if I may just interject, I wanted to just remind people that we can continue Q&A over Slack. So Laura, you're not off the hook yet.
No,
please,
I'm here.
Yeah,
I'm here.
Yeah, and please join me in thanking Laura and virtually clapping for her. That was an excellent tutorial. Thank you so much.
Thank you.
Thank you. And I guess just a general announcement that there are also, there are 4 more tutorials to follow in just about 10 minutes. Thank you again to everyone, and we can follow up with more questions on Slack.
And in the meantime, please feel free to join our RV Tavern. So the breakout room, you have the link on the program page, so you can socialize there. And of course, we have 4 more wonderful tutorials in about 12 minutes.
So where is this breakout room?
So if you go to the Slack channel, I think it's the first, it's the second one below general.
Hangout.
Yep, I think that's the one.
Okay. Ciao.
Ciao. Goodbye, everyone, and thank you, Sarah.
Thank you, Thomas. Thank you. Thank you, everyone. Bye.
Thank you. Bye.